Hello everyone, I'm Ho. It's my honor to be here to introduce our recent work, Detection and Reduction of Systematic Bias in High-throughput Rupture Experiment. This work is reported by me and my partner Xu Hui. I will introduce the experiment and the result of this work, and Xu Hui will introduce the theory used in this work. The supervisors are Jose, Zhigang, and Tongqing. This work is supported by the Air Force Office of Scientific Research. My report will be carried out from these four parts. The first is the background. The purpose of high-throughput experiment is to obtain a large amount of experimental data in a short time. But when we do a high-throughput experiment, we must think about the question, are these samples tested under nominally the same condition? We roll one die 100 times, or we roll 100 dice together. We call the experiment of the 100 dice as a high-throughput experiment. It's often assumed that these two experiments are equivalent, but this assumption is called into attention in our recent development of a high-throughput rupture experiment. In our previous work, we conducted a high-throughput rupture experiment as shown in this figure. 1,000 samples are pulled simultaneously by a climatic mechanism of 1 degree of freedom. We can see that the number of rupture samples in these two regions are very different. Similar problem also exists in other high-throughput experiments, such as the high-throughput experiments in biological field. Subsets of the measurements have different behavior. Many high-throughput experiments aims to test samples under nominally the same condition. However, whether a particular high-throughput experiment does so must be certified. Next, we talk about the methods. The first is how to test the systematic bias in a high-throughput experiment. Here we introduce a hypothesis test method called Anderson-Darling test. This method can compare the closeness of the cumulative distribution function of different subsets. And the long hypothesis is that samples in the K subset are independent and identically distributed. The calculation process of the Anderson-Darling test will be introduced by Xu Hui later. What we need to know now is that we can finally get a p-value from this method. And if the p-value is larger than 0.1, we cannot reject the null hypothesis. In our previous high-throughput experiment, samples are placed into 5 rows or 4 columns. The samples can be naturally divided into 5 subsets by rows or 4 subsets by columns. We can let k equals to 2 and perform a pairwise subset test to find which subset has a clear bias from the others. And we can also let k equals to the total number of subsets and perform a multiple subset test to judge if there is a significant systematic bias in the whole data set. We test the previous experimental data, where R1 and R2 refers to the first row and the second row, and the C1 and the C2 refers to the first column and second column. However, all the p-value calculated using the data of these 5 rows and 4 columns are smaller than 0.1, which indicated that the distribution of the 5 rows or 4 columns are significantly different. The above statistical analysis has shown that the data obtained in the previous high-throughput experiment are not RID. We checked the previous experimental setup and find 3 problems that cause the data inconsistency. First, the frictional force between the grips and the plates is insufficient. In the stretching process, the plates slip and the stretch applied to the samples as the left region and the right region become different. Second, the rigidity of the plates is insufficient. The plate may bend so that the stretch applied to the samples at the middle of the part and the side part become different. Third, the bracket consisting of bars and bearings cannot transform displacements to different rows of sample equally due to the insufficient rigidity of the bars and the low transmission of the bearings. For the sample preparation, we have also noticed another bench effect. In our experiment, samples are fabricated by the 3D printer. But after the 3D printer has prepared samples for several rounds of experiments, the samples of different rounds have different properties. For the experimental environment, we videotape the experiment and identify the rupture of the individual samples by image processing. The previous experiment was conducted in a change light. The uncontrolled light complicated the image processing. To resolve these problems, we improve the experiments as follows. To avoid slip, we fabricated grooves in the middle of the plates to interlock with the grooves of the grippers. To increase the rigidity of the plates, we replaced the material of the plates from aluminum to carbon steel and increased the thickness and the width of the plates. To ensure the climatic mechanism to apply equal displacement to samples in different rows, we replace the plastic bars with the aluminum bars and apply lubricating oil to the bearings. For the experimental environment, we videotape the experiment in a studio in which all background lights are broke. And for sample preparation, the differences between the samples in different rounds is minimized once we clean the 3D printer after printing samples for each round of the experiment. Then we use the new setup for the experiment. We first test 200 samples in one single row in one round of experiment. We divided the 200 samples into 4 columns. In the experiment, the 200 samples are pulled from the undeformed state until all samples rupture. The figure B plots the CDF of the rupture stretch of the 4 columns, and we perform the Anderson-Darling test using these 4 CDFs. The calculated p-value between every 2 columns and the p-value of the 4 subsets from the total sample set are all larger than 0.1. Therefore, we cannot reject the null hypothesis. Afterwards, we repeat the single row experiment 5 times to test whether there were differences in the results of different benches of experiments. The figure A plots the CDF of the rupture stretch of the 200 samples of one row in 5 rounds. And we use Anderson-Darling test again to calculate the pairwise p-value between every 2 rounds and the p-value of 5 subsets from the total sample set. They are much larger than 0.1. Also, we cannot reject the null hypothesis. But we tested 600 samples distributed in 3 rows. We can see that at the stretch equals to 2.331, 106 and 105 and 113 samples in the 3 rows rupture. And this stretch, the samples in the 3rd row rupture more than those in other 2 rows. We perform the Anderson-Darling test using these 3 CDFs of the 3 rows and the p-value calculated using the data of the row 3 are smaller than 0.1, which indicated that the distribution of this row is significantly different from other 2 rows. And we also calculate the p-value of the multiple sample sets from the total sample set. The calculated p-value is smaller than 0.1. Therefore, we reject the null hypothesis. The data from these 3 rows do not pass the Anderson-Darling test. Now we have the IID data. What advantage do this data have? We use the 1000 IID data from the 5 rounds of the improved experimental on one single row and the not IID data in our previous paper to fit the Weibull distribution. The fitting curve is marked with the black solid curve, and the 95% confidence interval marked with the 2 black dashed curve. And for the IID data, the confidence interval is narrow in the entire range of rupture stretch, and most of the experimental data lie within the confidence interval, which indicated that the Weibull distribution fits well to the entire range of the experimental data. But for the data reported in our previous paper, the figure B shows that the Weibull distribution does not fit well. For the real event rupture, we use the peak-over threshold method focus on the first 10 rupture samples. This method focuses on the statistics of the left tails by imposing a threshold stretch. We use the data close to left tail to fit the Weibull distribution and also plot a fitting curve and a 95% confidence interval. For IID data, the first 10 rupture data fell within the confidence interval, but for data reported in our previous paper, Figure B shows that the prediction of real events is not good. The peak over threshold method and the Weber fitting will be introduced by Xu later. In the previous analysis, we used 1,000 experimental data, but we will know that in the most engineering programs, we cannot obtain such a large amount of data, since the quality of data is improved in the present experiment. We test if we can predict the real event rupture by using a smaller data set. To get a small data set from the 1,000 test sample, so we randomly select 200 samples 6 times, and each time we use the peak over threshold method to get a threshold stretch, and below which 15 samples rupture out of the 200 samples. We use the first 15 rupture data to fit the Weber distribution and also calculate the 95% confidence interval. We found that the fitting result of the 6 selection are consistent. All the experimental data fell within the confidence interval. By comparison, the prediction of the real event using 200 samples in our previous experiments are not good. This confirms that when the quality of data is improved, the number of data needed to predict real event rupture with a higher accuracy and confidence can be reduced. Next is the conclusion. This work provides a procedure to improve the quality of data in a high-throughput experiment. Run the high-throughput experiment and use statistical method to test if the data of the high-throughput experiment are consistent with the IID assumption, and find out a source of the systematic bias and improve the experimental setup and iterate. The key of the process is to combine the statistical methods and the expertise in your research to design the experiment. And this is the end of my report. Thank you for listening. And then Xuhui will introduce the theory used in this work.
Hi, I'm Xuhui, and I'll be discussing the statistical methods used in our project. First, I'll be discussing the Anderson-Darling test used in our paper to test the systematic bias in high-throughput experiments. The Anderson-Darling test is a non-parametric method to quantify the closeness between empirical CDFs of multiple subsets of samples. So here, the data of a generic run of our experiment can be divided into several subsets, and we can calculate the empirical CDF of the ith subset of samples. We can also pull all the samples together and define the H sub n as the pooled empirical CDF. The Anderson-Darling statistics is defined as the sum of the weighted average of the discrepancy between each individual CDF and the pooled empirical CDF. Under the null hypothesis that all observations are independent and follows a common distribution, Schultz and Stephens show that the Anderson-Darling statistics converge to a limiting distribution given by the sum of a weighted sum of IID chi-square distributions. In practice, the experiment has only been run a few number of times, and the CDF of an actual run of the experiment can be used to compute an actual value of the statistics, and we denote by hat A squared. The p-value is defined as a probability that the theoretically distributed Anderson-Darling statistics exceeds the actual value. And if this p-value is smaller than some significant threshold alpha, we reject the null hypothesis and the samples in the case subsets are deemed not IID. If the p-value is greater than alpha, we cannot reject the null hypothesis, and the evidence is insufficient to deem that samples in the case subsets are not IID. Notice that there are multiple ways to test the null hypothesis, including the Kolmogorov-Smirnov test. Here we have chosen the Anderson-Darling test because the corresponding statistics magnifies the deviations in the tails more significantly than in the middle, and this feature is important in evaluating the real event rupture stretches. Next, I'll discussing the Weibull distribution fitting procedures. The rupture stretch can be assumed to follow a Weibull distribution, and in a Weibull distribution, we have alpha, beta, and gamma parameters that characterize the location, scale, and shape of the distribution. Given the data at hand, we can do two things. We can fit the curve by employing the maximum likelihood method, or we can use the peak over threshold method to predict the real event ruptures. And first, to fit the curve using the maximum likelihood method, we define the likelihood function by the Weibull density, which is the product of the PDF of the Weibull distribution evaluated at each individual rupture stretches. And we optimize over the parameters alpha, beta, and gamma to maximize the likelihood function. We carry out this procedure with the default numerical optimization methods in RStudio. To do real event rupture predictions, we can use a peak over threshold method, and following the likelihood of a Poisson point process, we can define a likelihood function with data near the real event as the first display in this page. Here, the lambda max is a threshold stretch, and n sub r is the total number of observations with stretches as smaller than lambda max. And to select the threshold stretch, lambda max, we can use the empirical mean residual life plots, which are defined in the next display. And lambda max are chosen such that for all u smaller than lambda max, the pairs of u, comma, e are approximately linear in this mean residual life plot. We carry out the maximum likelihood fitting to optimize over the parameters alpha, beta, gamma. Besides obtaining the fitted parameters, we can also obtain the confidence intervals follow the maximum likelihood theory. And we know from theory that the maximum likelihood estimators approximately obeys the multivariate normal distribution centered at the true underlying ground truth parameter theta, with a variance that can be approximated as the inverse of the sample Fisher information matrix. So we create the confidence intervals by sample parameters from the sampling distribution, and then inverting the cumulative distribution function to obtain the sampling distribution of the fitted stretches. And listed in here are three references that discusses the method that I described previously. And that's all my talk. Thank you for your attention.